All right, today we're going to cover talking about energy, heat flow, and then very briefly going over specific heat. So heat is specifically measurement of thermal energy. Remember, thermal energy is a type of kinetic energy. It has to do with the random motion of particles. So the more thermal energy that particles have, the more motion that they have, and we can measure that in terms of temperature. So thermal energy can be transferred from a system, which is just what the either a container is or the material that you're looking at, that you're focused on, its interaction with its surroundings as a result of a temperature difference. So in the image on the left, because the system is hotter than the surroundings, you're going to see that heat goes from the system to the surroundings. It can go into a system when that system is cooler than the surroundings, and we'll go into it. So we refer to ones that go out of a system when heat's transferred out as exothermic. Think of the word exit, so heat's exiting the system. And then when heat goes into a system due to its lower temperature, we say that it's endothermic. Think of into as endo in that case. So as you can see, temperature plays a big has a big impact on how heat is able to move or how that thermal energy can move. So heat flow or thermal energy is always going to travel from a hotter object to a colder object. So I say from where it's hot to where it's not. So if A has a higher temperature than material B, when they become in contact, heat's going to move from hot to cold. So it's going to transfer from the hotter material of A to the hotter material of B. So this is a common type of Regents question. So in a lab where the air temperature is 22, a steel cylinder is 100, it's submerged in a sample of water, how does heat flow through the system? So I usually say set up a little diagram, put each object down and write their temperatures. Then draw arrows. So remember, it's always going to move from where it's hotter to where it's colder. So the steel cylinder is hotter than both the air and water. So heat would flow from the steel to the air and also from the steel to the water. There's also a temperature difference between the water and the air. So heat's going to move from water and be transferred to the colder air. So we have a couple different things going on. We have heat that's flowing from the cylinder to the water and to the air, and that heat's also flowing from water to the air due to that temperature difference and how heat flows from where it's hot to where it's not. Just a little difference between heat and temperature. So heat measures the total kinetic energy. So it does depend on sample size. The more matter you have, the more energy that it has, the total amount of heat can increase. Temperature, however, is, remember, a measure of average kinetic energy. So it's taking an average of all the thermal energy in a sample, so it doesn't depend on sample size. So if we have a student that looks at two samples of ice, sample A has a mass of 10 grams, while sample B has a mass of 1 gram. If they're both at their freezing point, so at the same temperature, how do we compare and contrast the two samples in terms of their temperature and heat energy? So because they're at their freezing point and they're the same material, being at the same temperature, they're going to have the same average kinetic energy. However, when we talk about the amount or the total heat energy, because sample A has a higher mass, it's going to have more total heat energy, thermal energy. All right, we're also going to briefly mention specific heat. This is the next little section in your notes. Why did I do that? There we go. So not all materials actually increase or decrease in temperature at the same rates, or go up as high or drop in as low as each other. And this is because they have their own what's called specific heat capacity. So this value is the amount of heat it takes to raise the temperature of just 1 gram of that substance by 1 degrees Celsius or 1 Kelvin. So the lower that specific heat value is, the more quickly or more readily it's going to change temperature as it absorbs or releases heat, because that lower specific heat value is saying it just doesn't take as much heat for it to raise or lower 1 gram by 1 degree Celsius. We can use the specific heat capacity of water from table B in your reference tables. We'll come back to that when we do calorimetry. So for example, water has a specific heat capacity of 4.18 joules per gram Kelvin, and sand has one of 0.84 joules per gram Kelvin. If we have equal masses of water and sand, and they both absorb the same amount of heat, which material will increase the highest in temperature? So water only takes 4.18 joules for each of its grams to raise that 1 degree Celsius. Sand, it only takes 0.84 joules for each gram to raise 1 degree Celsius. So because of that, sand takes less energy for each gram to increase in temperature. It's going to increase in temperature faster and get to a higher temperature than water will. And that's related to its specific heat capacities. All right, that's it.